Hello, everyone. Welcome to the virtual Apache Druid Meetup featuring SuperAwesome and Imply. My name is Jelena Zenko. I am a community manager at Imply, and it's my pleasure to host today. Peter, would you mind advancing?
You can.
Thank you. So just a few ways to connect with the Apache Druid community and with Imply. First of all, if you're interested in finding out about more great meetups like this one, we actually have 36 Druid groups owned by Imply. So if you head on over to our meetup page, it's meetup.com/pro/Apache-Druid. You'll find all of our groups. We also promote all of our meetups on the Twitter page for Apache Druid, which is simply Druid.io. And we also announce all of the meetups on the ASF Slack channel. So feel free to join us there to hear about the latest and greatest. And also if you ever have any questions, that's a great place to go. We also love it if you go to LinkedIn, and if you're a Druid practitioner, if you add Apache Druid as a skill on there, in case you didn't know, you can do that. And then here we have a few other community resources, including our Druid community page at apache.org, and also our Google Groups user forum. I've seen quite a few folks on there. If you haven't joined that, that is also a really great way to get involved. And I'm about to hand the baton over to our first speaker. His name's Peter Marshall. He's based in the UK, and he is a technology evangelist at Imply, and he's going to be delivering our first presentation today. Thank you, Peter.
Thanks, Jelena. Okay, so that's a beautiful picture of me in a fantastic light. I'm sure you'll all agree. I'm a technology evangelist, as Jelena said, working with Imply. I've got a background of about 20 years experience as an enterprise architect. Don't hold that against me. And during that time, I've worked across lots of different technologies, from CRM through to master data management. I am qualified in theology and computer studies. But as I always say at meetups, please don't ask me questions about God, not unless we are able to meet each other and have a beer, and then we can talk about God. I am TOGAF certified, which sounds like I should be in an institution of some kind, but that's an enterprise architecture certification, some of you may know. I am an avid book collector, by which I mean that I buy books and then they sit on my shelf and I never read them. But I've got a lot of those. I also get told off for buying lots and lots of televisions and hi-fi equipment. For those of you who know, I am a believer in the prime Star Trek timeline. It's the only real timeline. And also for those who also know, #work. There's lots of places you can contact me. I've got a Twitter account. I've just started a Medium blog. That's my Medium address. And please email me if you've got any questions or you just want to make contact, peter.marshall@imply.io. So today, what am I going to be speaking about? I'm just going to be talking about the under the covers black box stuff behind Apache Druid. And many of you on the talk today may have heard this before. I apologize if you have. It's got a bit more information in it now about the latest versions of Druid. If you've got any questions for me particularly, I think, Jelena, we're taking questions at the end after the SuperAwesome talk.
Correct.
Cool. Okay, so a little bit of a background of Druid, what inspired it being created in the first place. Then we'll look at what's actually inside a Druid cluster with a few updates for Druid 0.18 and 0.19, which was released last week. And then talk a little bit about the data optimizations inside Druid and why it's such a cool thing. So Apache Druid, as it is now known, was originally developed at a company called MetaMarkets, based in San Francisco, who are an advertising exchange. An advertising exchange offers up space from various publishers, whether that's Facebook or some gaming platform, and then different advertisers around the world can bid on that space. And what they really want to know is whether or not they got a good click-through rate, whether it was presented to the right audience, etc., etc. And it's a very, very competitive market, extremely competitive market. And what MetaMarkets wanted to be able to do was to evidence to their customers that they were the best company in the world for placing your adverts with. And the issue that they faced was that as their company grew and they got more customers and more places to put advertising, they had a much increased growth in data. So we're not just talking about this being the usual volume, variety, velocity problem of big data. This was a real business problem for them. Their success meant they had much larger volumes of data being ingested and needed to be used for decision making. So they did a massive code and component level review of their architecture. And the result was the now infamous Apache Druid white paper. If you haven't read that, I do recommend going to read it. And what they said was that the existing technologies available on the market were stifling, and they made the data very stale. So when they were giving their dashboards and their user interfaces to their customers and to their account managers, they had very limited view of the columns and the information that's available. They had to filter that data, and it became very curated. And they also said that during the investigation, the engines that would generate the statistics, the kind of metrics that people want to know, had to be predetermined up front, and they had to limit those, because if they didn't limit them, then it took too long for the data to reach those people. And in other words, they had a very big problem with latency and with data throughput. So they decided that what they should do in the face of the unscalability, the disjointed view, the limit to the data, and the slowness of their data pipeline was to invent something new. And thank goodness we don't have to do that. I'm not clever enough for that. What they did was invented what was then at that time Druid, which if you look on druid.io is described as a high performance, real-time analytics database. That means that it's got capability of very high performance ingestion and very high performance when it comes to query execution. It's designed for real-time systems and data from the very start, i.e. event-based data, as well as handling batch data. It's got a focus on analytics, i.e. on doing counting, on ranking things, on generating general statistics, and it is in itself a database that is a very highly available, time-sharded, partitioned, columnarized, indexed, compressed, versioned, materialized view of the data that you've pushed into it, and enables these very fast performance on websites, on data science tools, and in traditional BI tooling. So this is the kind of thing that they developed. They developed a customer-facing portal where people can do ad hoc exploration of the different statistics that exist about the performance of their advertising. And it was also presented to their account managers who could have a conversation with their clients about performance, not that was 3 days old or even a day old, but actual live performance of campaigns, and to dig into it and have a conversation with that person and understand why certain things were happening. And this is something that they could not do with Hadoop, for example, because it was taking far too long to compute the statistics that they wanted to display on this page. And you know, those kind of tools just aren't built for the kind of real-time user experience that MetaMarkets produced. So a bit of a timeline for you. I mean, I will let you read this should you want to. It's being recorded. Please go and have a look. The key message for me about the Druid timeline is the rapidity with which Druid is maturing as an open source project. It's a real success story of the community coming together and contributing to something that is helpful for everybody, whether that is a bank in Turkey that is making policy decisions based on risk and liquidity information from markets, or whether it's a scientist in a university predicting bee colony collapse disorder across Europe, or whether it's Netflix making sure that you're definitely going to watch the next series of Stranger Things. It's a real community success story. And it's thanks to people like you on the call today, to software engineers who believe in the open source philosophy, and they are helping people every day make decisions faster and in a more full way than we can with tools that have existed for the last 25 years. So some key highlights in the recent version. The last time I gave this talk in person was in Munich. And at that time, we just, I think, released Druid 0.17. The big message in Druid 0.15 was the introduction of the data loader UI, which allows you to use a very familiar web interface to do the ingestion, to understand what's happening behind the scenes in the database. In Druid 17, we introduced Super Batch, which it sounds really cool. It is really cool. It really overhauled the way that batch ingestion is done in Druid. It made it more efficient, more options for parallelization. And we also introduced better SQL null handling. So SQL compatible null handling appeared in 17. 0.18, the big news was joins. Now I can execute a proper join statement in Druid SQL and then do lookups to tables that exist elsewhere in the Druid cluster. And that opens the door for anybody who's using something like Tableau or Looker to be able to just use native SQL queries to get at data and visualize it. Druid 19, lots and lots of cool things in Druid 19, but by far the coolest thing is query vectorization. What that translates into, without getting into the detail, is much faster query execution times. We've seen some queries speed up by 15 times over how they used to execute. So it's a fantastic success story. I get so excited about Druid. You probably tell I'm very excited about Druid. And I do really encourage everybody, go and have a look at the GitHub page, look at the pull requests, just see how active the community is. And of course, if you feel like contributing, I'd be very happy with that too. So this is the data loader interface. If you download any of the distributions of Druid, you'll be able to see this kind of interface. And I can build the ingestion configuration. I can pass my data, describe the schema, apply transformations and filters at ingestion time. And I can do roll up as well on ingestion. And I also get a view of the health of my cluster, so I can understand how well the tasks are executing. I can dig into the system tables now to go and have a look at how my segments are balanced and distributed, what size they are. And I can also do native SQL queries. So they've built this thing. What happens next? Well, their first interested customers were all in Silicon Valley, and one of those was Yahoo. And Tim Tully, who's the vice president of engineering at the time at Yahoo, said that, that Druid can do very large OLAP-style processing on the fly in hundreds of milliseconds instead of pre-calculating everything. And the performance is great. Some of the tables that we have internally in Druid have billions and billions of events in them, and we're scanning them in under a second. There's a link to the article at the bottom of this slide, and also there's the barcode at the top right there for you to scan. I'd like to just highlight three particular things about what Tim said. First of all, he recognized that Druid was good at OLAP style processing. That means that Druid is extremely good at giving you statistical information. Secondly, he highlights that Druid is about on-the-fly calculation. So in my pipeline that's Druid powered, I won't have created a data cube in any technology. I won't have processed my data in any way in order to generate statistics. Druid just does that for me on the fly. And that's a massive, massive impact for businesses who are dealing with large volumes of data especially. But it's also a big deal for people who want to deliver an ad hoc exploration experience. So I don't have to predefine what those measures are up front anymore. I don't have to sit down, oh, the bad memories. I don't have to sit down with people in the business and write a report specification and then go and craft a SQL. And then 3 weeks later, after we've argued about the report spec, finally come up with something they want. Now I can just give them an interface where they can slice and dice that data themselves and have that conversation with them. And thirdly, he mentions billions and billions of events, and you know, it's Yahoo. I was working with Advertising Exchange in Israel just a few months ago who are ingesting billions of events every hour. Druid is very, very scalable, but there are very small installations of Druid. I don't want you to be scared off by thinking Druid's only for big businesses like Yahoo. It's not. It's for anyone to go and have this kind of flexibility in their real-time analytics. So if I'm going to deploy Druid, where do I put it? Well, typically Druid sits after a data lake or message bus or in a data warehouse, and it powers the analytics engine that delivers applications sub-second statistical calculations and their combined real-time and historical data view. This slide is based on an article published by Fanjing Yang, who is our CEO. It's called The Big Data Zoo, available on the Imply blog. Please go and have a look. It's a good article and explains exactly where Druid fits in this zoo of different big data technologies that exist nowadays. So that's the Druid story. What is inside a Druid deployment when I actually get it? Where does it go? How scalable is it? How do I monitor the health of it? There are three families of processes inside a Druid cluster. There are query processes, which helpfully allow you to get the data out. Secondly, are data processes. Those are to do with ingestion, to do with storage, and actually doing the tasks that serve your statistics out. And then there are processes that look after the health and manage the tasks within inside a cluster. There are some prerequisites for the deployment of Druid, and one of those is called the deep storage. That's like a library of all the data that's available in Druid's format for these real-time statistical calculations. That could be in S3, Google Cloud Storage, HDFS, Azure Blob Storage, SQL Server even. There's a whole range of those. Go and have a look at druid.io and search for deep storage. You'll see all the compatible deep storage types. Then let's look at the processes here. So the first is the overlord process. That's handling all the ingestion tasks, and the coordinator processes are there to make sure the data's balanced, to distribute it well, and to enforce any replication rules that you have. That has another prerequisite, and that is the metadata database. By default, when you take open source Druid, it'll be using Darby, but you can use MySQL or PostgreSQL or any compatible database with those. Again, go and look at druid.apache.org, have a look for metadata storage. And another dependency is Zookeeper. Zookeeper is still used for the inter-process communications, for leader elections, etc., etc. So if I was going into production, I'd want 3 servers running those master processes. I'd want that because I get higher availability, but also it means I can do rolling upgrades on the cluster, taking each of my nodes down and bringing them back up again in sequence. Excuse me. So let's look at the data processes. The first data process is the middle manager process, and that's responsible for all the ingestion. And it's also responsible for questions about the very freshest of data that comes in. And that data can come through batch ingestion, or it can come in through streaming ingestion like Kafka or Kinesis. And there's a whole list of different compatible front-end databases, whether that's Postgres, whether it's HTTP, and that list is expanding all the time. Azure and GCP connections were made available just in the last few versions natively within inside Druid. So this data is coming in. What happens next? Well, after a period of time, say an hour, or after the data's reached a particular size, it comes out of this initial buffer, if you like, and we hand off into deep storage where it's fully version controlled and becomes immutable. And all of this work is being tracked within the master servers. And this is really important for exactly once ingestion for Kafka and for Kinesis, which are guaranteed within Druid, because this process, this workflow is carefully orchestrated around the topic offset to make sure we guarantee that exactly once ingestion. Excuse me. The master processes then have heard that there's some new data available, and it will load those into the second type of data process called the historical. And the historical is then responsible for loading those segments from the deep storage onto its own local storage. And from there, the historicals then take over answering questions about this slightly older data. And those rules are aware of the health of the cluster, they're aware of the balance of the cluster, and they also enforce any replication that needs to take place across the cluster as a whole. The infrastructure in Druid is built to be very elastic. So for example, as my data grows, I might add more historical servers. And in general, when I'm working with people, I always recommend at least 2. 3 is better because you get a higher degree of parallelism when queries are executed. The largest cluster that I know of has 500 terabytes of data in it. That's nearly 50 petabytes of raw data, which still blows a little bit, but it's that scalable. One of the other things that I can do inside Druid is I can say, well, okay, after data has reached a particular age, I'm going to put this onto a different set of servers. That means you infrastructure guys, you can control the cost benefit you're actually getting, because we know data that's older, people probably don't look at that as often, and we put that onto a machine with fewer cores or less local storage or less memory, for example. Some of these ingestion tasks are what we call splittable. They're parallelizable. So that could be from web, S3, Azure Blob Storage, a range of different ones, and including HDFS. So I could do something very clever here. I can have multiple middle managers running, and I can scale up my ingestion linearly. So I can have 10, 50, even 100,000 events per second per core. In fact, I've seen a cluster that has 3 million events per second going into it. And that's how I scale my, my ingestion out. So in summary then, the data is ingested, it's served immediately by middle managers, often in parallel, and the data is handed off into deep storage, and then there are rules that are fired that then send the data off to the different historicals, which could be tiered. So how do I actually get at this data? What's the query processing like? Well, Druid is fantastic for time scan, group by, top N, and search type queries, be issued in one of 2 ways. Those of us who are familiar with Druid remember the days when it all had to be executed using Druid JSON. And for those of us who love JSON, it's fantastic. But now we've moved natively to a SQL interface powered by Apache Calcite that is a fantastic SQL language. Once I've sent something to the cluster, it goes to the broker node, and the broker process is responsible for distributing all the tasks to execute the queries, responsible for consolidating the results that come back, and it also does a level of post-processing as well. So one of the fantastic new additions in the latest versions of Druid is the use of query lanes. What that means is that when a query comes in, I can programmatically, or by using a setup in the cluster configuration itself, determine sets of queries that will skip the queue. In other words, I want to issue this query and I want it to be answered right now before all the others. This query broker, when it's received a request for some statistics, goes to the master server and it says, hey, where's the data to answer this question? Well, the first option is it's going to be something that's just come in right now. So those results come back from the middle managers before they're then sent off back to the requester. But the other place it can come from, of course, is from the historicals. So the historicals are holding this slightly older data. And again, those results are sent back to the broker. When it's in the middle managers, it's in a row-wise in-memory data store. So it's very, very quick to get those results back. Whereas data that is coming from the historicals is initially loaded on disk and then brought out of disk, put into memory, and then held there in a memory mapped cache. So what that means is, in the fantastic situation of frequently used data, or if you've got a lot of memory in your clusters and your historicals, is that you get these statistical queries executed in memory in parallel, which translates to just ridiculously fast query performance. Typically, you'll get, say, 10 data servers for every query broker. And you can add more historicals and more managers as your data increases, or if you need greater parallelization. Joining happens inside each of these individual processes. So when the query is executed, it goes off, does a key value pair lookup or an index table lookup. That's really useful for bringing back results and enriching it in real time within the query execution. So the data comes back, post calculations are done, and then it's sent back to the requester. Notice that as these queries execute, they're all executed discretely. There's no cross-node chatter between any of these processes, and which reduces our network overhead. And because the data is immutable, it means that there's no locking, there's no recalculation, there's no redistribution of the data as these queries are executing. So in addition to us having a low network chatter, we also have in-memory stores, and we also have within Druid query caching for results as well. In other words, it's very, very fast, and I love it. So TLS enables encryption for all the data in motion that passes between these nodes. And of course, you can use encryption in the deep store and the metadata database as well to really harden the installation. And from the outset, Apache Druid was built to be extensible. It's a core value of the development community there. So if you do come across a type of deep storage or metadata database or even a source system, or you want to do something weird with a weird aggregation, you want to go and look up to something else, you can do that by writing particular extensions. And that's been very successful in the data science community, where there are companies who, like Polefish, have contributed interfaces for a range of different tools. So we've got a Python, an R, a Scala, an Erlang interface to the database as well. So again, people really recognize how awesome Druid is, and we all want to try and make this better. So please, please go and have a look at how you can contribute and be part of this community. Druid will also emit metrics. There's a range of different metrics emitters. They're essential, in my experience of working with Druid, in understanding exactly what's going on. What are the query performance metrics that you want to meet? How well are the queries executing? Where are they executing? What's the health of the cluster overall? So it's one thing that's often missed in a Druid deployment, but I do highly recommend you do go and think about how you're going to get the metrics out again. So that's a Druid cluster. What happens to the actual data that goes in? Well, the data inside Druid is highly optimized for OLAP queries. It's kind of a combination of time series and columnar and search approaches to the data to make sure that we optimize what is a very good format for writing data into one that's good for reading. So Druid shards its data according to time first, and creates for us this like series of things called segments. And each of those segments can be sub-partitioned. So perhaps they'll be partitioned by a hash or a range in batch ingestion, or maybe you'll use the existing sharding in Kafka or Kinesis. The configuration for all of this is called inside the ingestion specification in JSON format, but now we've got the data loader, it's brilliant. That specifies the source format, the segment period, the dimensions, the row filters, any transforms that you want to do. And it's this process that also columnarizes and dictionary encodes and bitmap indexes and compresses the data. So I can take my row-wise data, columnarize it. For those of you who are familiar with shorthand, it's effectively one of the things that Druid does. It will take a column, take text values, and create an integer index that's brilliant for top N and group by calculations. And it creates a binary version of that row, understanding where the data is within the rows, which is great for doing and, or, and not binary operations. So I can end up with a set of dimensions, great for filtering and sorting and doing functions, but I can also create windowed aggregations. So in conversation with the business, maybe it's not so important that I have each individual row, but that I create blocks of time, and then I calculate, for example, the sum stock exchange or the maximum satisfaction figure for that period. And if I use something called data sketches, which is a Yahoo project, go and have a look how data sketches work. Instead of recording each individual visitor, let's say their IP address or maybe their account name, I can turn that into a data sketch. Here I'm using a hyperlog data sketch, which allows me to estimate very, very well what the, say, distinct count is. But I can also do set operations. I can also do quantiles. So I can take what was quite a large data set and shrink it down, and I end up with very, very small scan times. I end up with very highly optimized storage and a massive query performance. So that's the data inside Druid. And I have to say, it's fantastic. The result in many cases that is that people can get rid of pre-computation. They can even get rid of some stream processing that they're doing. They can reduce the complexity of the ETL jobs. But it's important to note, Druid is not just a columnar database. I've seen articles where people are like, oh, Druid's the new columnar database. It's not just that. It's not even just the new time series database. It's not just the new data warehouse. It's important to realize it's a combination of these three things we've learned in the big data world for the last, goodness knows, 10 years, something like that. It is a time-sharded, columnarized, OLAP optimized data store, and it's suited very well to on-demand real-time statistics on very fast arriving data and at scale as well. To use it well, you'll need other people. That's why the community's here. Please do as Yelena's recommended, please go and look at the Druid user forums, look at the Druid community meetups around you, join ASF Slack, you'll see me on there, my colleague Matt and Rachel as well. And please download a distribution, give it a go. There's the Apache distribution and also the Imply analytics platform distribution. And follow us all on Twitter. And that's me. Thanks, Yelena.
Thanks, Peter, for delivering a most excellent presentation. Next up, we have Saidul Bashar. I apologize if I'm mispronouncing that. Saidul, I'll give you an opportunity to say it the correct way. Saidul works at SuperAwesome, and he'll be delivering our next portion of the meetup. And if you just wouldn't mind saving all your questions for both Peter and Saidul until the end. Thank you.
Thank you, Jelena. You actually pronounced my name correctly, so there's nothing to correct.
Hey, great.
So yeah, thanks. So hi, everyone. Thank you for joining this presentation. Today, I'm going to explain how SuperAwesome migrated Druid with zero downtime. So I'll start the presentation with kind of explaining who SuperAwesome is, what we do as a business. Then I'll move on to explaining how our infrastructure is set up. And then I'll finally talk about how we migrated Druid with zero downtime. So let's start. So SuperAwesome is the #1 kid tech company in the world. And our mission is making the internet safer for kids. So let's discuss what it means to make internet safer. So every time a kid goes online and every time they use a mobile or a tablet or a computer, every time they go on a website, there are a lot of network requests that are happening. There are a lot of digital information that are being transferred. These digital transactions that are happening are not always kid safe. So what do I mean by kid safe? Basically, they're not always designed with privacy in mind, and they are not always designed with responsible design in mind for kids. So our mission is to make sure that a lot of these things are designed with kids in mind and they're kid safe. So we identify and build products to make kids' digital transactions safer. Some of our products are verified parental consent flows to allow the collection of personal data in a way that is compliant and responsible. Making zero data ads that ensure that no kids' data is tracked and only contextual ads are provided. We are protecting kids' social media engagement by providing kids-safe social media platforms. Today, we protect 12 billion kit safe transactions every month. And this is increasingly going over time. We're trusted by 300 top kids brand and content owners. So now let's start talking about why we wanted to do the Druid migration and what was our plan. So we had a very old Druid version running on our old Kubernetes cluster. And we wanted to move to the latest version of Druid and also move to the latest version of Kubernetes. So we decided to do this in 2 steps. The first step was to move to the latest version of Kubernetes and then with the old version of Druid. And then the next step is to upgrade Druid on the new version of Kubernetes. So this talk is going to cover how we move from the old version of Kubernetes to the new version of Kubernetes. So for us to do the migration, we had some constraints that we needed to take into account. So the first constraint was that we wanted to move to a new AWS account. So for our old Druid cluster was in an AWS account where it was being used by other services as well. This made cost analysis for the Druid services more difficult. And it also meant that there was no separation between services. Moving to a separate AWS account will ensure that we could do better cost analysis and we have better separation. Because all of our other services are running on Kubernetes, we wanted to run Druid on Kubernetes as well, as it was being run on Kubernetes before. So that was another constraint. Also, we wanted to migrate Druid with 0 downtime. So we rely on live analytics to deliver our products, so we couldn't have any downtime while we are migrating Druid. So I'm going to talk a bit about infrastructure as code. So all of our infrastructure is managed as infrastructure as code. The advantage of having infrastructure as code is all the infrastructure is written in code. So there is a single source of truth. So you can go in Git and you can see what the infrastructure configuration is. The infrastructure is immutable, so you don't have updates in place happening. Basically, you declare the infrastructure in a declarative language, and the tools then take care of how it will deploy them. This also helps us maintain environment parity. So the difference between our staging system and production systems are some variables, so that there are probably less instances in staging and more instances in production, but they can be deployed from the same script by changing the variables. So this gives us confidence that staging and production are very similar. You can also leverage diffs quite well with infrastructure as code. Basically, you can plan your infrastructure deployment. You can see what resources are going to change. Then you can decide whether the plan is right and the right resources are created. Then you can go ahead and deploy them. If you see any problem, then you can update your code and then see the plan again and continue doing this. You also have one-way data flow, so there's no feedback loop. So how do we do infrastructure as code? So we deploy all of our services in AWS on Kubernetes, and we use standard AWS services. So outside Kubernetes, we use Terraform to set up most of our AWS resources. And inside Kubernetes, we use Helm to manage our AWS templates. So why did we want to migrate Kubernetes? What were the benefits and what was the problem in the first place? So as you can see from the architecture diagram, Kubernetes actually has lots of services. And so it has master nodes and worker nodes. In our previous setup, we were managing both the master node and worker nodes. Everything was managed by us. it increased management overhead. It also increased cost for us. We decided to move to Amazon EKS. With Amazon EKS, the master node is managed by Amazon. So we don't have any management overhead. It also reduces cost for us. We only manage the worker nodes. The next issue was the previous setup wasn't, the previous Kubernetes setup wasn't done using infrastructure as code. It was basically done with lots of scripts. So this meant that we didn't get all the benefits of infrastructure as code. So we couldn't predict how upgrades are going to look like, whether something is going to break if we upgrade, because we could only see the changes once the changes were done. With the EKS migration, this was not a problem any longer because everything was set up with using infrastructure as code on Terraform. So we could plan our changes, we could see what the changes are going to look like, and then apply them. This made sure that we didn't have any concern about upgrades, so there was no downtime. It also saved us cost-wise to move onto Amazon EKS. So I'm going to talk a little bit about Helm. We use Helm for infrastructure as code inside Kubernetes. We have our whole Druid cluster on one Helm chart. The Druid components run on stateful sets so that we can give them persistent volume. So our Druid components themselves are stateless. Things like the middle manager, historical overloads, all of them are stateless, but running them on a stateful set helps us when the ports restart, the middle managers and historicals can recover faster because they already have access to the data on disk. We run reindexing jobs on our using Kubernetes jobs. So this helps us with job failure. So if there is any job failure, then they can be rerun automatically. This also helps us monitor our jobs and see problems. Our services talk to each other using domain names. So this is quite important for us because when we are using the domain name, if port for middle manager or historical goes down and the IP address for the port changes, overload then knows that this is still the same middle manager, even though the IP address changed. So now I'm going to talk a bit about our old Druid set, how it was done. So our old Druid setup was deployed on an AWS account sharing with other services on a Kubernetes cluster. The deep storage was done on S3. And our segment metadata was saved on MySQL RDS. Our Kafka setup was running on AWS MSK, Amazon Managed Streaming Service. So the first thing we did for the migration was to move, create a new AWS account and copy the S3 data to the new S3 account. So there were a few things that we needed to consider for the S3 copy. The first thing was AWS permissions. So with AWS accounts, by default, different accounts don't have access to each other's buckets. This is very good for security reasons, but this was a problem for us because we needed to copy the S3 bucket from one account to another. Pardon me. So the way we solved this was we updated the bucket policy on the old S3 bucket to allow our sync script to read from it and write to the new new account. We also used AWS profiles to use the credentials for the two different AWS accounts in the same script. The next issue was syncing S3 buckets can be very slow. In our case, we had staging with 300 gigabyte data, which took probably a day or two. But then our production had over 30 terabyte of data, and it was taking days. So we did a few things to resolve this issue. The first problem why this happens is with S3 sync command, the sync command needs to go through all the files that are in the bucket and decide whether it needs to sync the files or not. So if you start syncing and for some reason the sync stops, it takes a long time for the syncing to start again. In our case, when we were running it on production, it was taking over 30 minutes to start syncing. So we did two things to resolve this. The first was to basically write a script. So the data was saved in S3 in different folders based on timestamp and data sources. So we could write a script that would pick up the data sources and different time ranges and copy the data across, which meant that if for some reason the script died, we could just start from where we left off, and we could do smaller time so that we could run things parallelly as well for different time ranges and date ranges. We also used Kubernetes. Used Kubernetes to run the sync. This helped us leverage AWS networking. So basically, if we ran the sync command from our own systems and not used AWS network, that would have introduced a lot of network delay. Because we were running it in Kubernetes, it meant that we were using the same network. The data transfer was a lot faster. Druid is still, the third issue was that Druid is still creating segments during the S3 sync. So we wanted to make sure that all the data was copied once and only once. We should not have any missing data or duplicates. So in this case, we didn't have to do anything because the historical segments are immutable. Our system was configured to keep the old data and new segments when the data was reindexed. So we knew that we would be able to recover everything if there was any issue. But just to be sure, we disabled reindexing processes during the migration. The second thing is segments are still mutable when they're being created. We knew that we would not have these segments on new systems, but we were sure that the data would be reindexed from Kafka. So because Druid stores the offset, so there was not going to be any problem. So just to recap, the issues that we had to fix when we were copying the S3 buckets was AWS permission, syncing S3 buckets, slowness, and creating new segments while we are copying the data. So I'm also providing a bit of code snippet of what we did so that if anyone wants to use them, they can. Line number 2 here shows how we copied the entire S3 bucket using AWS profiles. And after that, the next section basically shows the script that we wrote to copy the S3 bucket with different dates. The next step was for us to copy the segment metadata to the new cluster. Copying the segment metadata is very important because the coordinator finds out where the deep storage is and all the other information from the segment metadata. Our next step was to copy this. There were a few things that we needed to consider when we were copying the segment metadata. The first thing is statefulness. So we didn't know if MySQL was storing anything that was specific to the cluster. So we needed to find out how to resolve this. So we took samples of from the different tables, and then we identified cluster-specific data so that we could address them. The second thing was MySQL was had references to the deep storage, and we needed to change this when we moved to the new cluster. So the way we did this was we dumped the MySQL data and then we replaced all references to the clusters and the deep storage. And then we uploaded that data and created a new database in the new AWS account. This way we managed to make sure that everything was targeting to the right cluster. So just to recap, the two issues that we had to solve for segment metadata migration was statefulness and references to buckets. So I am providing a code snippet for how we did this. So the first bit of code shows how we dumped the MySQL data, then searched and replaced all the references to old bucket with the new bucket. The next bit of code shows how we then created the new database and tested that the right references are in place. So here we can see that the two tables that specifically had references to the old bucket was Druid segments and Druid task logs. The reason that these two scripts are separate is once we download the MySQL data, in our case, we had 50 gig of data and it was taking a while. While we are downloading the MySQL data, the S3 sync is still happening. So we needed to make sure that after we've downloaded the metadata, we then make sure that the gap between before we did the sync and after we downloaded the metadata is synced again. So the buckets are synced again. Then we run the update so that everything is kind of in sync. The next step was for us to set up the new Kubernetes cluster and deploy Druid in that cluster. So this was very straightforward because we had our Helm chart to deploy our Druid setup, and we used the same Helm chart. We changed the references to the deep storage and the segment metadata, and we checked the diff, and then we could just deploy it. So this wasn't that difficult. There are a few things that I need to cover here. What happened to Kafka indexing and how did we make sure that the indexing was done properly? So Druid doesn't store the offsets in Kafka. Druid stores the offsets in the segment metadata. The problem with not storing the offsets in Kafka is that we can't then monitor the Druid consumers the same way that we are monitoring our Kafka consumers, our other Kafka consumers. But the good thing about that is this means that our segment metadata basically have the offsets of when the data was dumped, and as soon as we start the new cluster, it just picks up consuming data from where it is stopped. So we know for sure that there was not going to be any differences. So in this slide, I talk a bit about the statefulness and how we kind of managed Druid, the Kafka statefulness by consuming from the offsets that we stopped consuming before. The other issue that we had was indexing. We weren't sure that we would get exactly the same data on both clusters. So the way we resolved it was we ensured that data stayed in Kafka for longer than the duration of the migration. The new cluster took a few hours to catch up. The new clusters therefore had different segments for the same time period, but these segments contained the same data. So that was it. Now we had the new Druid cluster setup side by side with the old Druid cluster setup. So this enabled us to kind of keep the old setup running and then have a new setup. Then we could test both the old setup and new setup side by side. So the first thing we needed to consider was routing. So we wanted to test the new cluster without affecting existing users. What we did was we bypassed the DNS resolution to be able to run queries against the old and new clusters at the same time and check that the responses were identical. So we had a set of test cases where our test cases were going through the broker and then making sure that it could query the middle manager for a particular range, and it could query historical for a particular range. So we run the same set of queries for both the old cluster and new cluster. And then we compared the data to make sure that there was no differences between the data. We also kind of asked other teams that are using Druid to run their own set of test cases against the new cluster to make sure that all the test cases that were running and passing against the old cluster are running and passing against the new cluster. So as I mentioned, the main thing that we needed to consider for testing is how we manage the routing. So I am providing a code snippet here to show how we use the curl resolve command to use the same URL for both the old Druid cluster and the new Druid cluster, so that the queries themselves don't change at all. But the queries for the URL can go to the new Druid cluster by resolving the IP address. Once we were happy with all the tests and we were happy that there is no difference between the data query responses coming from the old cluster and new cluster, we simply had to switch the DNS in AWS, and all Druid queries for Druid users were then forwarded to the new cluster. This was very seamless because it was just a DNS switch. And that's it. We were very confident that everything was going smoothly. Now we could take down the whole cluster. So thank you. That was how we migrated Druid with zero downtime. If you have any questions, that's our next session. So please feel free to ask me.
Thank you, Saidul, for presenting your use case. Looks like we have a few questions in chat that haven't been answered yet. I'm going to assume they're for you since they came in while you were speaking. And maybe you or Nicholas can answer it. The first one is from Ivan. It's on a medium-sized cluster, roughly what will be the maximum supported cardinality of a dimension? Let's suppose that you have 1,000 dimensions.
So from the Druid API documentation that I have looked into, the recommended cardinality is 100. But from my understanding and from what I have read, there are companies who are using thousands of dimensions as well. In our case, our cardinality isn't that big. It is less than 50.
Okay, and sorry, that question might not have been for you. That was for Peter. The one from Olga. Does Druid offer any optimizations for forecasting, and are there any examples available?
So I'll take that one. Yeah. So I believe there is another meetup that's just happened where someone has integrated Facebook Profit specifically for forecasting. I'm not going to say who I think it was because I can't remember correctly, but it was someone in the advertising space and both Facebook Profit and Yahoo Sherlock for anomaly detection. There's examples in the community where people have plugged those two things in. Yeah, and just to reinforce again, yeah, so I mean, I've seen people put 150 dimensions into Druid. I mean, it's a columnar database, right? So, you know, it's columnar, but those segments that I spoke about, those segments do get quite large. You end up with larger scan times. So yeah, you just have to be very careful. What I see people do rather is that they will have, there's a publishing company in Germany who do this. They will have several data sets with the dimensions that people really need in the application that you're trying to build. It's just part of the design exercise that you need to go through. And look out for an upcoming blog on that topic shortly, Yelena.
That's right.
It's going on my list.
Great. So we're opening it up to any other questions. Feel free to unmute yourself if you have a question and specify whether it's for Peter or Saidul. Can't take everyone at once. Okay, well, we've got one on chat. This is from Petri. Can Druid handle non-sequential time series data sets, i.e. update segments as new data sources come online?
I think I'm going to answer your question. If I'm not, please put it in chat and I'll try and answer it. Yes, you can do updates inside Druid. Again, go and look at the Druid docs for that. You can do that via batch ingestion or streaming ingestion. In fact, Itai, who's on the call here, has got a fantastic article on updates in Druid and a very clever way you can use some of the features on ingestion to do row by row updates. So it's very cool. But yes, you can. So I see that with late arriving data especially, and also where people want to make queries on the latest data as quickly as possible. That's what's most important for their business. But then they want to kind of color that later. Maybe you'd have some kind of prediction algorithm out in Spark somewhere that's going to go and do something on the data and then color it afterwards. And yeah, so for example, they would put that into S3 and then load that data from S3 to replace the data that's already there. I think that answers the question.
Okay, well, if that doesn't answer the question, speak up now or forever hold your peace.
Petri, connect with me on LinkedIn. More than happy. We can have a chat on there.
Great.
There's a question for you there, from Madhav. If you have to redesign awesome architecture again, would you use Druid or something else? I'll answer that. Yes, of course he'd use Druid. That's one for you, I think.
Saidul. Yeah.
Yes, I will use Druid.
Yay!
Anyone else in the chat box, or feel free to unmute yourself. We can take a few more questions. Well, we've got a little bit of a quiet group today. Well, for those of you who will be watching this later, if you weren't able to attend today, always feel free to connect with Peter on LinkedIn. You can also connect with Saidul as well. I hope that's okay, Saidul. And also you can go on ASF Slack and ask questions there anytime, as well as the Druid user group, the Google user group, which Peter referenced earlier. He had a nice slide with all those links. Peter, maybe we'll put those back up just to close.
Yeah, sure. Yeah.
Thank you, Peter.
Thanks, Elena. I also wanted to say, yeah, I'll be very happy to help anyone if they're doing Druid migration and they have any questions. I'm available on LinkedIn.
Fantastic. And I believe, hopefully, we're going to be planning another virtual meetup with our friends at SuperAwesome. Thank you to the entire team over there for making this meetup possible. We really appreciate it. And I'm sure everyone really enjoyed hearing more about your use case and migration today. Really great talks. And keep an eye on the Imply Druid meetup groups page, and we'll be announcing our next meetup soon. Thank you, everyone. Thanks, Peter. Thank you, Saidul. Thanks, Nicholas, Itai, and anyone else who helped us answer some questions today.
Yeah, thank you.
All right, bye-bye.